Let's begin by looking at the general setup of the problem, where we will define the problem. In general, for the nonlinear case, we have second order differential equation written in this form. The second derivative of y in time, let's say, denoted as y double prime, is in general given by some function of time, y itself, and the first derivative. In general, this is a nonlinear function. That's the differential equation. And typically, we also have some initial conditions given. And since it's a second order differential equation, typically we have two initial conditions. Initial condition for the value of y itself, y at some time t0 is equal to y0. And then the rate of change of y, or the slope of y in time at time t equal to t0, is also given as y0 prime. So y0 and y0 prime are two known numbers that we know which prescribe the initial condition. And so this problem, the differential equation and the initial condition together, define what is called the initial value problem, where we know the value of the solution and its slope and is governed by a second order differential equation. So two initial conditions and the differential equations complete the specification. So having looked at the nonlinear problem, let's simplify it to the linear case, and we're going to encounter general linear second order differential equations quite often. And so if this differential equation, this function f, is a linear function of its arguments, y and y prime, we can write it in this general form, y double prime plus some function p of t times y prime plus some different function q of time possibly times y equals a known right hand side g of t, which is yet another third arbitrary function. So that describes the general form of a linear second order differential equation. And here in red, we can contrast it to a very common second order differential equation, which I'm sure you have encountered in many examples. For example, that of a mass spring a damper system. You may be a particle displacement, or you may be the position of a sports ball, or maybe position of a planet, or maybe other physical variable satisfying this differential equation. So to complete the specification of the initial value problem, again we have the same conditions, that the value of the function and its time derivative at time t equal to 0 are both given, and that describes the initial value problem for the general linear second order differential equation. We also commonly encounter a different kind of problem, which we call a boundary value problem. In a boundary value problem, the value of the function may be known at 2 points for a second order differential equation. Y is known at t equals t1 to be some value y1, and the value at some different time t2 is known to be some other value y2. And so we have two pieces of information that are known, but they are known at different times. They are not known at the same time. And for example, it could also be that we know y at a particular time, and then we know its rate of change at a different time, t2, and so on. So these constitute a boundary value problem. So let's just think about this physically in the context of a particular example. If you think about the trajectory of some sports ball, a baseball that has been hit, if we know the velocity of the ball and its position, so the rate of change and its position at some initial time, that describes the initial value problem. But if we know something else about, such as we know the position of the ball at two different times, but we don't know the initial velocity, that describes a boundary value problem. We now want to introduce a shorthand, an operator form for writing the differential equation. And so here, if we denote by capital D a shorthand for the rate of change in time, d dt is capital D is a shorthand for that, then this second order general linear differential equation can be put in a compact form like this using this operator L, where L is defined in this way. So L involves the second derivative operator d applied twice plus p times the first derivative operator d plus this arbitrary function q that describes the operator L, which is in general a second order linear operator. That operating on y being forced by right hand side g of t, which is a known function that describes the same second order equation, just written in a slightly different form. All right. And so we can proceed to consider the case when the forcing is 0, when the right-hand side vanishes. If g of t is 0, then we have a homogeneous differential equation. This right-hand side would vanish, so we have Ly equal to 0. There is no forcing present. And so the homogeneous part of the equation also is very useful in solving the inhomogeneous equation. So we will see that as we proceed.